wait for the discussion. Now, I would like to, so we can thank again Lorenzo for his presentation. I would like to welcome now Grzegorz WROCHNA. He's coming from Poland. We know him, he has participated in several activities that we are doing at the open level. I would like to mention the Sustainable Nuclear Energy Technology Platforms, but he's also involved in governing boards of the GRC or the Euratom Program Committee. He has been working also at CERN and has a PhD in physics and worked for 8 years, I think, at CERN in the 90s. Please, the floor is yours. Thank you again.
Thank you very much. Well, previous speakers, they have presented a broad portfolio of big, wonderful projects, and I have only 2 tiny projects to present with not so fancy acronyms, NC2I-R, GEMINI-PLUS. But those are the 2 most important projects presented at this conference. And I'm going to convince you about this in a minute. Look at this diagram. This is the fuel consumption, fuel in different forms. Electricity, we are very much concerned with electricity. It's only 18% of the energy we use. All the rest, over 80%, we use for heat, household heating, for industry, and for transport. And all that today is high emission sources, mostly fossil fuels. So to address this 80%, we need nuclear reactors producing high temperature heat for the industry. We need nuclear reactors producing heat which could be used then to produce hydrogen for electric cars powered with fuel cells, because lithium-ion batteries, I mean, it's just a temporary solution, I believe. So most of the other projects presented at this conference, they address this tiny 18%. And those 2 projects, they address remaining 80% of the need. What kind of tools we have to meet this challenge? Well, in Europe, we have, first of all, the SET plan, Strategic Energy Technology Plan, covering different energy production technologies. And we have European technology innovation platforms behind each of the technology. For nuclear, we have Sustainable Nuclear Energy Technology Platform, having 3 pillars, and one of that is Nuclear Cogeneration Industrial Initiative. The mission of NC2I is to contribute to clean and competitive energy beyond electricity by facilitating deployment of nuclear cogeneration plants. So you see, our goal is not just an R&D. We aim at the deployment of the nuclear reactors for the industry, for household heating, for production of hydrogen, and so on. And to be most effective, we concentrated on single technology, high-temperature gas-cooled reactor. What is very specific for this technology is a TRISO fuel. When uranium is inside a little balls covered with silicon carbide. So this is in fact an accident-tolerant fuel developed many, many, many years ago. And thanks to that, the reactor has an intrinsic safety features. So in case of accident, if all the coolant is lost, the reactor cool down by itself, I mean just by conduction and radiative heat transfer. So no core damage is possible, so there is essentially no need for exclusion zone. So the coolant is helium, 750, 850 degrees. There is experience with reactors with even 950 degrees centigrades. A nice features of this reactor is that it's quite flexible. It can operate at different temperatures. It can produce heat and electricity with different proportions. It could be easily adapted to different industrial needs. And what we would like to concentrate now is to provide the steam of 550 degrees centigrade, which is widely used in the industry and even for electricity production today. This is somehow ready to be deployed. But for the future, of course, we think of higher temperatures too. So what is the challenge here? It is not the technology. Technology is well proven by a number of experimental reactors, even commercial reactors. 2 big reactors are now being commissioning in China. The challenge is, in fact, in the business model mainly. Because the technology is available for more than 30 years, and the HTGRs are still not widely used today. So the question is why? What are the barriers? Who are the potential users? I mean, how big is the market? What business model should be used to introduce them? How to license those reactors? What is the optimal deployment path, and so on and so forth? Those kind of questions are addressed by those 2, as I said, most important projects, NC2I-R and GEMINI-PLUS. NC2I-R was running in 2013 to 15, a little bit less than 2 million euro, and GEMINI-PLUS is running now. We have just submitted a report after half of the project, about 4 million euro. So NC2I-R is conducted by the consortium which is shown on the map. Here, in addition to Europe, we have also South Africa having big experience with designing and starting the construction of HTR. Unfortunately, the project was not finished there. It is coordinated by NCBJ from Poland. This is coordination and support activities only, but still I believe that we have achieved quite important goals in this project. The project structure is based on 4 work packages. The first one was to analyze what are the perspectives of NC2I, what kind of forum we should have, and then what should be the international cooperation to prepare in the best possible way for the first HTGR design and construction. And I will show you some results later on. The second work package was the mapping of European industrial institutions, about European institutions having experience and facilities useful for practical implementation of nuclear cogeneration, especially for the industry. The third work package was about safety and licensing, again including mapping of experience gained so far, suggesting licensing procedure for nuclear cogeneration unit and so forth. And then finally was the fourth work package, a roadmap for a demonstrator, including data from other work packages, study of various industrial scenarios and business model. So you see this project was aim of gathering all information which was already developed in many different projects, many different places all over the world, and then trying to combine it so in a package when we can start real work on the real design of the first reactor. Just an example of the results, we made a survey of more than 130 sites in Europe, mostly chemical industries. We asked them many questions. The most important one, what is the electric power they need, and what is the thermal power we need? You can see this on the graph here. And you see very important trend, namely, smaller the reactor, bigger the market. So you have to find an optimum, and an optimum seems to be around 200 megawatt thermal, something between 150, 330 or so. And I would like to focus on the specific case on Poland, because in my country, just 13 largest chemical plants have today installed more than 6,500 megawatt of heat in this temperature range. So if you want to replace those coal-fired or gas-fired boilers, I mean, then you can save something like 5 million tons of fossil fuels. And it seems that the reactor giving an output of 165 megawatt thermal is what fits all the need, because this is the size of the standard gas-fired and coal-fired boilers used in our industry. And if we estimate what is the need for the industrial heat, so in Poland we could fit something like 10 to 20 reactors by 2050, in Europe 100 to 200, and in the world 1,000 to 2,000. Again, you see how important those projects are. We also have a number of cogeneration units, again mainly coal-fired today, of the order of 200 megawatt electric, and they cannot be replaced by big light water reactors because they're distributed in many locations. And okay, for the electricity you can move them far away, but not for the heat distribution. And the second reason is that they are very often close to industrial installation or even habitating areas. And then there is increasing potential for hydrogen. We have in Poland a factory of hydrogen buses called Ursus in the city of Lublin, and they are selling thousands of buses all over Europe. So there is a big need in Poland, and therefore Polish government took quite seriously the results of the NC2I-R projects. In the year 2016, Minister of Energy appointed a committee to study the possible implementation of high-temperature reactors in Poland. The members of the committee were mainly from the industry, both engineering and end users. I mean, chemical factories like Orlen, like Azoty. Orlen is a refinery. Enea Tauron is our energy-producing, electricity-producing utilities, having a lot of cogeneration plants, and KGHM is copper mining, the biggest energy consumer in Poland, in fact. And the report was published, and you can find it on the internet. And after that, the Minister of Energy has given a green light to the implementation of the conclusions. And recently, we've got from the government roughly €4 million to start to prepare a legal framework for that. We need to change the law in Poland. We need to develop the way to license those reactors. And we need to develop TSO framework. We need to develop some tools and procedures to test materials, components, and so on and so forth. So then, what is the results of the work of the committee is that in addition of the commercial reactor, we need also an experimental reactor, say 10 megawatt or something, not as a technology demonstrator, but rather, to get experience, to be, a test bed for the licensing and so on and so forth. But then we have to go immediately for the design and construction of the commercial reactor. What is very important is that we split the process into two phases. We cannot ask today end users to make investment decision. The level of risk is too high. So we want to engage them in the design of the reactor. If we get, say, 4 partners, if the design work takes 5 years, if the half of the money is provided by the states, then each partner needs to bring something like €4 million a year, which is a very tiny fraction of the incomes usually. And this can be done from OPEX money, R&D money, in fact, and does not require the investment decision. The investment decision can be done 5 years from now, when much more is known about the gas market, about the coal market, CO2 prices, and the reactor itself. So in this situation, we have started the second project I'm going to talk to you about, namely GEMINI-PLUS. Gemini, because it's a partnership between the twin organizations, NC2I in Europe and NGNP Industrial Alliance in US, and the plus is because in addition we have JEA from Japan and Kaori from Korea. So you see the partnership is quite strong here, again coordinated by NCBJ from Poland, 3 years time, launched September 2017. And here you can see 5 strategic objectives of the GEMINI-PLUS project. The first one is obvious: a nuclear solution to address European energy objectives according to the set plan, clean energy for Europe, safe and sufficient use of nuclear energy, secure European energy supply, and industrial jobs in Europe. There are 4 packages in addition to those related to organization and dissemination. The first one is devoted to safety I mean, precisely to the licensing framework. Especially we want to address new regulations, post-Fukushima regulations, EU nuclear directives, and so on. The second one, very important, is about the conceptual design. I mean, we want to have the reference configuration, something which will be possible to deploy both in Europe and US, and it will be a starting point for real design of the reactor. The third package is about innovations. The innovations are not to make it more fancy, on the contrary, to make it cheaper. And the fourth work package is about the deployment. Again, as I said, we need some novel business models. We need to see what is the possible supply chain, what is the spent fuel management, and so on and so forth. During this projects, I mean, we met several challenges. Just tell you a few examples. I mean, we are dealing with really innovating safety approach. I mean, we have two ways to go. We can design a reactor with the safety features like the ones from LWRs, and it could be easily licensed, but then it would be very expensive. But then we try to explore the specific features of the HTGR, like the TRISO fuel, okay? The silicon carbide on the TRISO is the first barrier, in fact. And if we try to explore those features, I mean, we can largely reduce the cost of the reactor. Then we need to break economy of the scale, because larger reactors are cheaper per megawatt. How to break it? Well, first, by cogeneration. We use all the energy, not just electricity. Second, we count on large market. And the third one, it must be an SMR. That means factory produced and fast assembly online. But in order to achieve that, it must be universal. So the same design must fit to different applications. Steam for chemical factory, cogenerations, and hydrogen production, for example. What is very important from the licensing point of view, that we have to separate the safety case of the reactor from the safety case of the chemical installation. I mean, if we mix the two, I mean, we will never license this kind of reactors. And here is the first result. I mean, the first scheme. How can we imagine such a system? Basic requirements for that. What you see is the reactor. It is connected to the chemical installation or to cogeneration turbines just by one pipe with the steam. To be independent, we have even our own small turbine, so the nuclear island is completely independent from the user side. So it can be easily plugged into industrial networks, just replacing old boilers. And of course, and we heavily rely on all passive safety features. And concerning the size of the core, the size of the vessel, everything is designed in such a way that it could be transportable by road. But this is not the end. We already started to think about new projects for up, because we have now new Euratom coal. So we would like to continue in three directions. We need to strengthen the license acceptability. So we would like to really continue the work on the unique safety features of the reactor. Then we have to make it more attractive for the industry, and especially, you know, I'm talking about the hydrogen supply. And not just by making this, I mean, 1,000 degrees or something like that, but also there are new ways to produce hydrogen at low temperatures. We need to study all those. And finally, we want to improve its political and societal acceptability. I mean, we are talking about proliferation issues. We about, you know, possible use of the reactor to destroy plutonium minor actinides, improving long-term stability of nuclear energy by employing Tollier cycle, and this kind of innovative futures we want to address in the future projects being now prepared. So if by chance some of you will be a referee of these new projects, you know this is the project which deserves 15 points. Thank you.
Thank you, Gregor, for this overview. So you see only 2 projects, but still the same time as Lorenzo. It's okay, it was very interesting. Question, 1 or 2?
Thank you. Thank you very much for this update. It's not completely new also from an IEA perspective. But you mentioned a very point that I would like some clarification. That in order to be viable, I understand, and not to go into a complicated safety case, the safety of the reactor should be considered completely independent from the safety of the chemical plant, correct? Right. Does it mean that, for instance, there is no need to develop a specific safety requirement and safety guidelines for the coupling of these 2 reactors? That the regulation, they don't have even to talk one each other, because physically there is just a piping between the two plants. Maybe I don't know exactly how it works as a coupling, but in any case I understand that these 2 plants, I mean the nuclear power plant and the chemical plant, will be on the same site, and on top of that the HDGR doesn't have a containment, because you say there is no risk of melting because of the triso particle. So you have a nuclear power plant in the same site with the hydrogen production, which of course has safety-related issue. The reactor has no containment, and you don't consider any scenario in which you have an interaction to be considered from the safety regulation viewpoint. Is it correct?
That is absolutely correct. When we started to investigate possible influence of an accident in a chemical factory, for example, on the reactor or vice versa, I mean, we go, I mean, to a real mess. I mean, on the chemical factory, you get, for example, a big ammonium tank, and if this tank is broken, all people die in 5 minutes. So, really, if we start to consider initiators on the chemical side, we are lost. So the idea is to have just to have them on the same side, I mean, but separated by, say, 800 meters or so, having a hill in between and just the pipe going through. So in a normal system, when you have trip on a turbine, it affects the reactor, okay? It should not be the case here, because we connect this to existing steam networks of the chemical plant, and they have their own inner ways to deal with the variable load, variable need for the steam. Okay. So on the other side, we have our own turbine for producing electricity for the own needs of the reactor. So again, we do not rely on anything external here. This is, I believe, the most important and rather difficult constraints which came out of our study from those 2 projects.